Are you turning down lights? Yeah. Okay. Okay. Well, hello, welcome everybody.
Hey, welcome.
We don't do our work with all these high-tech toys that, our high-tech toy is a snorkel. But hopefully I'll get to show you some cool stuff and you'll get as excited about seagrass as I have been over the last 20 years. So let me make sure I can make everything work. The big question, I guess, is why seagrass? Why are seagrasses important to what we do? And I mean, if you really think about it, in the estuary in the Indian River Lagoon, seagrasses are the backbone of everything. Everything either relies on seagrass either for a nursery or for their development or where they actually go to breed. The fish come in from the ocean. We also have species that will eat the seagrasses and rely on the seagrasses to be there for that. And then we have the species that rely on the decaying parts of the seagrasses. So the entire stages of the seagrasses and all the animals that rely on it create the whole lagoon system and keep everything in check. And there really is a balances of checks going on out there all the time as species come and go and things happen on times throughout the years. So we're often asked at the water management, what's the economic value? Everybody wants to put an economic value and the dollar amount on seagrasses. So Bob Bernstein, who was my supervisor for 15 years at the water management, has come up with a formula, and we've all kind of tweaked his formula because, you know, different amounts of the economic value, different times, you know, you want to keep, it kind of goes up and down, and we've settled on this one right now. So if you think about that there's maybe 500 million macroinvertebrates out there living in the grasses and over 40,000 fish, then you can kind of work a formula. And, you know, it's kind of, you know, it's got its little places for error and things. But, you know, if you take the value of the fisheries is a big part of it, how much people spend to come and go fish. Then you start taking fractions of different things out there, and then at the end, divide it totally by the acreage of seagrass that's available. And so we've kind of come up with a number that is around $10,000 per acre of seagrass. And when you consider out in the Indian River Lagoon, we have between different years, different times, we've had between 50 and 70,000 acres of seagrass lagoon-wide, and that's from, you know, Ponce all the way down to Jupiter. That comes out to about $500 to $700 million a year. So there's a different, now you say why seagrasses, there's a different part of that. So as a biologist, why seagrasses? I have my little part about all the animals and everybody needing it for different aspects of their life cycle, but also there's a huge economic value of it. So at the water management, what do we do? What is our charge? And how are we going to manage this valuable resource? So our basic ecological model this is very basic, okay? And then we can expand from here. And so basically, you have our watershed loading. We have all the nutrients and we have everything coming in. And we have our sunlight. We can't control sunlight, so we work on the watershed loading, okay? We have the water quality. And then eventually it gets down to the seagrass. So by decreasing and keeping the watershed loading at a minimum, we can keep the water clarity and the water conditions up, and the seagrasses will continue to grow. Simple, basic model, okay? But if we kind of expand on that a little bit, we have things that happen, okay? We have set seagrass targets, and so we know that seagrass can grow to a certain depth. But if you continue to have runoff, and we continue to add nutrients, and we have phytoplankton blooms out there, that deep edge of seagrass will continue to recede and get shallower and shallower over the years. And you can see the problem, what happens is as the grass starts dying and goes shallow and shallower, it starts releasing its own nutrients that are withheld within it, and you have epiphytes and you have macroalgae. And so you almost wind up with this continuing decline if the water quality conditions don't improve. So our whole work is trying to make sure that we avoid situations like this, okay? We're going to kind of end our story today with maybe not such a happy story, but we're going to try and, this is our main goal at the water management. The lagoon is big, Okay, so what we've had to do in a way to manage the lagoon is we have to subdivide the lagoon. You can't, it's very hard. We do have lagoon-wide averages. We do use those numbers, and it will give you an overall, are things improving lagoon-wide, and that's always good to know. But we subdivide the lagoon. So you have the sub-lagoons is what we call them. Mosquito Lagoon, Banana River, and then the Indian River proper is further subdivided into the north, central, and southern lagoon. And as you know, I work for St. John's Water Management District. We share the lagoon with South Florida Water Management District. So South Florida starts right about here, a little bit further north. But so there's a couple of little things that, we try to work together on a lot of projects, but it's government, and, that's not always easy. So we're not going there. Okay. So we have our sublagoons, but then we further divide the lagoon into segments. And each one of the segments help us. Within each segment, we have water quality stations and we have seagrass monitoring stations. And that helps us look at more defined areas when we can, you don't necessarily want to pinpoint and say, okay, you did this. But you do have certain water treatment plants, sewage treatment plants, and you also have hydrodynamic features that divide the lagoon into even smaller segments. So we have these now. We combine segments, we group them, we average data differently, but we have the opportunity to subdivide things even further. So within our seagrass monitoring program, we kind of use a hierarchical tiered effect. We base things on both spatial and temporal scales. And so our bottom would be our lagoon-wide mapping. We take aerial photography, we do it every 2 to 3 years, and from there we get basically a footprint of the seagrass beds throughout the lagoon. And so that would be our base from there. And so how we use that data a lot of times is we can just basically graph, and let me see if I can use this pointer. We can graph, and of course, I talked about acres of seagrass, and now I'm really going to mess with you, and I'm going to tell you about hectares of seagrass. So basically, a hectare is 2.5 times the amount of acres, so it's 2.47 acres. So it's a hectare. So if you kind of think, the 25 here is the 75, what we've wound up with 75,000 acres of seagrass, okay? So you can see we have our 1943, which is our historical coverage that we've used over the years as our target area, our target for seagrass acreage in the lagoon. And you can see in the beginning when we started doing some of our mapping efforts, we were not at our historical target. And over the years, we have actually exceeded the 1943 coverage. Now that doesn't mean the entire lagoon has exceeded that. Some areas have grown more than other areas. Some areas have receded due to development, and those areas will not probably ever recover to what it was in 43 because of the development that is there. Okay? But you can see over the years, we've kind of had some leveling off, then we have some growth periods, and then maybe some more leveling off. But this is what we use basically as our mapping to monitor seagrasses on a long-term trend as far as back to 1943. And how you can do that, in a GIS, in a geographical information, you can take those coverages and you can lay each year on top of each other, and we can watch how the beds are very dynamic, and you can watch how the beds may be receding and growing out into deeper areas. And you can see how it doesn't always cover the same footprint all the time. For whatever reason, the grasses might not expand into all the areas they were. But when you get out to current times, they had at least exceeded most of the beds where they had ever been mapped before. So what we do with that a lot with our mapping coverage is we have set deep edge seagrass targets, because where that edge crosses, where the mapped edge of the bed is, we can layer in the GIS system on top of a bathymetry. And so here we have bathymetry, and here we have depth zones. So if you think of as the darker blue, we're getting deeper in the water. So we overlay our seagrass coverages, and you can see we have our 1943 is the red, and then I just picked a current year, okay? And then we run fake transects in the computer on top of the bed, and we can project down into that bathymetry layer and determine what the deep edge of the bed is. And then we monitor that over the years. Every time we do a new mapping coverage, we can see if we're reaching our depth targets of where the seagrass bed should be growing to, according to the water quality and everything in that area. So some of the sublagoons have better depth targets than other other areas. Okay? So that's how we use our seagrass mapping. But then we needed to look at things at a little finer scale because the seagrass maps don't tell us the density of the grass. We don't really see what's within the bed. We cannot look at species at that level. So we set up a more fixed transect monitoring where you're actually in the water and you're monitoring the beds individually. So from all the way from Mosquito Lagoon to Jupiter, we originally in 1994 set up 74 transects. And since then, we've added some in areas where we've needed to watch a little more closely. So we are up to 100. So we have 100 sites that we monitor twice a year, summer, winter. And basically, you can see we go from shore, pretty much perpendicular from shore, and we go out to the deep edge of the grass bed as well, as another check to make sure that the mapping, which is done at 1 to 24,000, 1 to 24,000 feet, to make sure that that's also we're seeing the same edge of the bed. So we basically, along our transect line, we run out, we put down our grid, and we do all non-destructive sampling because we're out there a lot, and we're out there throughout the whole lagoon. We don't take samples from the field. We've developed a lot of visual estimates and counts. We use different agencies. A lot of people help us do this. So we want to make sure that we just came up with a nice visual methods to continually go back to these sites over years and years. So you can see we have 100 squares. And so you count presence, absence, we do all the different species that are there, and you do canopy heights, you do macroalgae, and make general notes of whatever's happening along that bed. So we also, the thing is these 7 species. We have 7 species throughout the lagoon, the most diverse estuary in the entire country, so makes us the best. But it's very important to see that. You wouldn't see that at a mapping level. So you can see Haliduli up in the top is our most predominant species. That's the shoal grass. You pretty much see it. It kind of would look like St. Augustine grass. And then we have the manatee grass, Syringodium, which is kind of cylindrical if you ever get out in the grass beds. And then the turtle grass, the thicker, the Thalassia testudinum, which is more of a tropical, subtropical species. And then we have our 3 species of Halophila. Halophila johnsonii, which is the only seagrass to be federally protected. It's on the threatened species list, and we have that here, right here in Fort Pierce. And then we have paddlegrass, Halophila decipiens, my favorite, Halophila anglemanii, stargrass. It's so cute, just starry all up there. And then Rupia maritima is widgeon grass, which typically you don't find in this area of the lagoon. You find it further north. But a very pioneer species, comes and goes, different times, not always present, but it counts as one of our 7 that we have available. And those 7 species, their distribution without the lagoon, you can see if you go across each one of my transects, I've kind of shown how they're distributed throughout. And you can see Haliduli wrightii in blue is found at almost every single transect throughout the lagoon. Now, Syringodium in red typically likes clear water and salty water. So once you start getting into areas like Cocoa Beach, Melbourne, and this area, you don't typically find Syringodium because it doesn't like the fluctuating salinity that occurs in that area. But as soon as you start getting down towards the inlets, you start getting a lot more Syringodium. And then Thalassia we find typically south of Sebastian. It's where the break from temperate and subtropical species occur. So we have Thalassia found here. Typically, it also likes the inlet areas as well. And then you have Rupia, which is typically found more in the northern section. And then your 3 Halophila species. Anglemanii is found throughout the entire lagoon, but decipiens and johnsonii are also subtropical species found from Sebastian south. So if I bring back my graph with my seagrass mapping and overlay my transect data. Now this is the transect, this is the entire length of the transect, the distance from shore. And this is one of our most valuable parameters in our transect monitoring because that's what also we'll use to be able to tell us the health of the beds as the beds are growing out into deeper water. So you can see that since 1994, we've kind of been tracking, we've had a large growth during this time, and then we kind of leveled off for a number of years, just the same as the mapping years did. And then we had another large growth growing out into deeper beds. And then here we've been kind of stabilized for the last couple of years. So these two programs at different scales are matching each other very well. And we see the positive trend. So now we're going to start kind of breaking that down. Because of the transects, I can start dividing things down into a little bit more finer scales. So we're going to look at the transects, that total distance from shore, the transect length, at a sublagoon, okay? So what I've done is I've taken all my distances, all my lengths, and I've kind of binned them into these groupings, all right? So if you kind of think of this color coding, darker blue, we're getting longer beds, okay? So basically the same as that graph, that line had shown, as we set up the beds, the colors are getting darker in those final years as the beds were growing into deeper waters, okay? And you see, by looking at this, everything looks very stable. It's a large scale, so you don't see as much of the variability occurring at this large scale. But as we start moving down into a finer scale, now we start looking at things at the segment level. So we have everything subdivided into the segments. You can see how from year to year, sometimes you wind up getting some changes. You know, the beds will start coming and going. But overall, if you really look at this, you do notice that there are darker colors out towards the end of the years, okay, with years on the bottom. Now, also, you can see that there's areas of very stable. Mosquito Lagoon and North Banana River, very stable areas. You have very little growth, very little development. You have very little freshwater inflows, no canals. Everything's built fine. And North Indian River, here, you have very little growth. Same thing. So this whole area we kind of use a lot for our stable. That's more of our natural systems. And we use that to kind of monitor what natural variability is occurring that's really outside of any influences that are going on. But you can see once you start getting down towards Melbourne and that area, you can see there's a lot more variability occurring from year to year. Okay? And then once you get towards the inlets, things start settling down again. The inlets do help a lot to flush a lot of things. Unfortunately, a lot of things get flushed in and out of the inlets. Then, if you take it down to a site scale, so like I told you, I have 100 sites now, you can see that you have a lot more data. Okay, but don't try to look, I mean, you're going to drive yourself crazy. All you're basically looking is kind of the same. You look at the color schemes, okay? You can see how this is still very stable, even all the sites. So all these sites were averaged together in the very beginning on the first graph that gave you the Mosquito Lagoon sublagoon, okay? But you start seeing you have some areas with a lot more variability. You're back here in that Melbourne area and Cocoa Beach, and you have a lot more ups and downs. But you have some very stable areas, Sebastian area, and then once you get further south, things are very, very stable. So if I was going to end my story, see ya, get off the stage, you think, cool, seagrasses are doing great out there, right? Someone already heard this story. Well, unfortunately, even though the beds have been growing out into deeper water, in the last 8 years or so, we started noticing that when we'd put our grids down, instead of getting a beautiful grid like this, we wind up getting grids like this. So what seems to be happening is, even though the beds are expanding into deeper water, there is a thinning. The beds are getting less dense within the bed themselves. Okay, so this made us start thinking about adding things at another level. So back to the same graph, okay, we've seen this now. So I've added, you've got the overall footprint of the beds, and then we have our transects. But when I add now the density, the percent cover of what's actually occurring in that bed, you see that even though the beds have been expanding at this time, we're seeing a declining that's occurring within the beds. Okay, so this has really gotten our attention. We started seeing this, and you watch things for a while and go, it's going to turn around, it's going to turn around, it's going to stop, and it didn't. So then we decided that we needed to start monitoring stuff at a finer scale. So looking at this on the density, this is basically the same kind of graph that you've been looking at, but instead of distance now, this is percent cover. So I've kind of binned, but it's still the basic idea that you're looking for darker colors is higher density. Okay, so as in the earlier slides, you saw darker colors on this end, and the current years, now we're seeing lighter colors. So we see here that we had much darker colors when we first originally set up the sites. But there's still areas, Mosquito Lagoon, North Banana River, still staying very, very stable. It's really when you get down into the Melbourne and the Cocoa Beach and these areas where you really start seeing a lot more variability and decline. So our third tier is we started taking our transects at a monthly. Instead of just doing some of them, or instead of doing all of them just summer, winter, we have about 15 of them now that we do monthly. Because we needed to see when, because we'd go back to these sites in the winter and there'd be a huge change. And we didn't see what happened throughout the fall. And we all know that typically during the fall season, we have our storms and we have more rain events occurring. So what's happening is when we sample them in the summertime, something happened between July and then when we went back out there in January. So there's such a decline, and then when we go back again, they've even further declined. So we want to watch how these are declining throughout the time period. So with our monthly sampling, I'm just going to show you an example of a couple of them. We're able to get some of that signature that happens, more of a seasonal signature throughout the year. So at first, okay, so Mosquito Lagoon. Remember, Mosquito Lagoon is our very stable area that we've been watching over time. So this is all of this area, Mosquito Lagoon, average. So this is about 7 transects averaged in to get these numbers here. But you can see, basically, the red line here is the distance from shore, and the blue line is the density. And you can see that basically the transects have stayed about the same length. But the density has been pretty similar. It's still very high. It's above 50%, which is very good. 50% cover is a good density to have, okay? But then now we're going to look at one of our sites, one particular site. And you can see here, the same scales here, the distance from shore, very, very stable. No seasonality to that distance at all. A lot of areas we've sometimes found that the beds would kind of go back and forth, summer, winter, summer, winter. But up in Mosquito Lagoon, they managed to keep the same distance throughout the entire year. And here you can see, we started this one in 2008. You can see that here's January, so we go summer and then back to winter and then summer and winter, and you can see that we were able to see this. So this is our natural, what we should expect to see at our other sites. You know, this is what is going on, natural variability. So when we come further down into Melbourne, I'm trying not to give Melbourne a bad name, but we do have to say it. All right, we have Melbourne. Now this is the same thing. This is the average of about 7 transects as well. This is for this whole segment here. And you can see we have a lot more variability. You can pick out the times where you had big events, big rain events, okay? So you have the beds going up and down here was the droughts that we had way back in the late 90s, and then it started raining around 2000, and the beds died back. But they came back, they recovered. We're not going to talk about this yet. Okay, so the blue line, the density, you can see here now, instead of being above 50%, we're below 50%. 50% is your best of times. But you can see here the decline that's occurring. Even though the bed was still growing out into deeper water or stabilizing, we saw that this decline was occurring in all of the beds there. And at one of the sites, you can see originally here we have summer, winter, summer, winter. But we started the monthlies right here because we saw this decline even in the length of the bed occurring here, and that was during this period. So we started adding this one as a monthly. And you can follow this one along. Here's the hurricanes. So everything died back, but they came right back after the hurricanes. Here's 2006. Everything was back. We were looking good. Everything seemed stable. This is FAU, Tropical Storm FAU. And everything dropped down, and then it came right back. So it's like, this is the way things should respond to this. So it was nice to have that information so that we didn't go and come back and see that there was everything gone, and then it'd take a while to come back. Okay? But you still see that we have this decline occurring here, and we've had this now in 2011. Sebastian, this last one I'm going to show you. I know, I could go on and on. I love, these are my babies. My son is only 16, so, I've been doing these for 17, 18 years now, so they're my babies. I tell my son that. These are my oldest children. So, okay, so Sebastian's very stable. It's at the inlet, right? So when we average all the sites here at Sebastian, you can see it's been very, very stable. But this one you can particularly see, even though this has been stable, the decline in the density has been occurring. And this is the thinning of the beds. And then when we look at one of our particular sites, this was our summer, winter. We started doing this one monthly, about here, and you can start seeing how it's come. It was fine, but it made this drop. All of a sudden, it had always been up around 70% cover, and then it dropped down to about 40%. And then it stayed there for a long time, and then recently we've had further decline. And I'm sure if any of you spend any time on the water, you're seeing some changes out there right now. So originally, when we started seeing this decline in our data, we were able to kind of attribute it to salinity. At the time, we were having a lot more storms. The storms were coming in the fall. And the lagoon has a very long residence time, especially in the northern areas. So when we would get some of these big rain events, like the 2004 hurricanes and then Tropical Storm Faye, the fresh water can stay in that area for up to a year. So that's a long time that these grasses are trying to live in very low, less than 20 parts per thousand. Ideal, they really like 25 to 30. Ocean water is 35. So what we were able to do is be able to, with our data, be able to say, the beds that had the lower salinity, around the 20, had less density. And the higher, our beds that were more stable, like Mosquito Lagoon, North Banana River, in that area, where the salinity would stay more stable, we were able to keep our densities at much higher levels. So 60% of that can be explained, 60% of the change can be explained by salinity alone. So originally, low salinity we were thinking was a problem. So let's look at salinity for a second. Salinity is a basic element of what seawater, of estuarine water, estuaries have. An estuary is typically with fresh water coming in and salt water mixing, right? That's natural occurring out there. So you have constantly fresh and salt. Well, you can see now this data is lagoon-wide. This is an average of a lot of areas of the lagoon. And you can see that it is not something that stays very stable over time. So you have ranges from 20 parts per thousand up to over 30 and close to 35 parts per thousand during different times of the year. And if you really see, okay, if I go back to my geologist in me, I love looking at long-term trends. So if you squint, you can see, and it's there. Dennis doesn't want to believe me, and I'm glad he's not here, because he says it's not there. But I think there's like almost a 10-year cycle in these peaks in salinity. Okay, so yeah. We're not going to talk about that one. But the other ones, well, I don't know what happened there. But then recently, we have been under very, very high salinity in the last year. Since 2010, our salinity has actually gotten into the 40s, which is in the northern part of the lagoon, which has really not been recorded before in that area. So we don't want to overlook salinity. And even if we go back up into my Mosquito Lagoon, I keep going back there, that's what's telling me my natural variability. And this is now monthly data. Okay, that other one was annual means. But looking at monthly data, you can see that even from month to month to month, and within a year, we have ups and downs. But overall, there still is this kind of decadal trend that could be occurring out there. So that one we're using as a natural background of what the other sites have going on besides any other freshwater influences that may be coming from all the tributaries. So can you see that one? Is it clear? That's typically what we used to, typically we'd see in the lagoon. So now we're going to talk about 2011. If anyone's been out on a boat, if you've been north of here, this water's still pretty down here. If you've been up in the northern part of the lagoon has gone from looking like that to kind of looking like this. And unfortunately, it started around February and March of 2011, and it persisted throughout the year. And the beautiful lagoon kind of became this nasty pea green kind of color. And you can see where I have some satellite photos here from you. It turns out it wasn't just one particular species of phytoplankton. This turned out to be a suite of species, mostly chlorophytes, These are species that, it's not an invasive species, it's not a harmful algal bloom. You'll hear that HAB, harmful algal bloom things. These did not have a toxic stage to them. These are species that have been found in the lagoon forever. They've always been in very, very low concentrations because these species are marine species, meaning that they like higher than 35 parts per thousand. Well, you saw the salinity graph. The salinity in the last year has been going much higher than 35 up into the 40s and staying in the 40s. We have not had rain in a long time. And so that just allowed this species to take off in these areas. And it possibly may have started, this is Banana River, this is the ports, the cruise ships up in the Banana River, and then coming down into Banana, you can see that lovely color. And that's in April, by April. Really in March, we started getting the chlorophyll numbers higher. By May, and these are true color photography from the satellites, you can see it became this beautiful fluorescent color. And it managed to spread throughout. And if you'll know, at the port here, you have the barge canal that connects the Banana River to the Indian River. So then, by May, this bloom started getting into the Indian River as well. And this one, you can hardly see, but by August, this is still very, very green. You can see there's some cloud cover there, but basically it's still just as green. So we kept thinking, okay, it's going to stop, but it just kept going and going. And what happened is, if you remember from the graph in the beginning with the nutrients coming in and the runoff and everything, as the grasses and everything else out there started dying, you have all the macroalgae and you have everything starts dying, it starts feeding. It continues to feed this phytoplankton bloom. And as itself continues to turn over and dies and reproduces and keeps going. So you have this continuant nutrient pool that's out there turning over and continuing to keep this going for months and months and months. So, and actually this is from the Fish and Wildlife Service. They would put out these reports, and so they were able to run some of their models through, and they would give them these colors, and they call it a probable bloom. I mean, this is more than probable at this level. But you can see by July, we had it all through Banana River, it had gone into Indian River, and then it was working its way into Mosquito Lagoon. So this has still been going on, and you can see in this last photo, now, this is January, this is just last month, that it's starting to clear up, finally, in the Banana River and most of Indian River. But you can still see there's still traces because it took the longest to get up into Mosquito Lagoon. It really didn't get up into Mosquito Lagoon until about August or September. So it didn't seem to, so it's having a longer effect. It's still kind of growing up there. But it didn't have an effect on the grasses up in Mosquito Lagoon because it came at the end of the growing season for the seagrasses. But throughout the rest of the lagoon, we're going to see some changes now. So you know, you want to say that's what caused this, but it's very, very difficult to put your finger on any particular thing. We've had a number of things, and maybe it's everything just happened to fall, you know. You don't want to use the cliche of, you know, unfortunate events or, you know, everything just happened to come aligned. The planets just came aligned, and all these things just fell into place at the right or really the wrong time. And so one of the things that we're looking at is, if you remember, we had 2 very, very cold winters. And you can see one of the coldest winters we've had in a long, long time was the 2010 winter. So these are your water temperatures. And you can see, and it's one of the things, and I know we're not going to get into any other kind of what's going on out in the world, but one of the things you'll constantly hear scientists talk about are the extremes. And you can see the extremes too. You'll say, this is the hottest of now, or this is the coldest. And that's really what starts changing in a system. It's the extremes that can have an event that can start things cascading downward. And so we have, all of a sudden, we have some higher temperatures and some of the coldest temperatures. And so some of these large swings may be what some of the factors that went into this event. We've also, some of the nutrients, phosphorus is one of the nutrients that we monitor all the time. And you can see over the years, we've been working on getting these phosphorus numbers down, right? And it's been working. But all of a sudden, what happened, what caused this is what we're still trying to figure out now. Was there something that everything started releasing nutrients at one time? Did one of the events from the cold event, did things die? I mean, remember, we're temperate and subtropical. Things aren't used to going down to 4 degrees centigrade or down to into the 40 degrees Fahrenheit. I mean, that's cold water. These, just like your outside plants, they're going to die. So different things are going to be dying, and when they die, they release nutrients. So this isn't necessarily caused by some sewage treatment plant that all of a sudden dumped all of effluent out there. The nitrogen itself also has been declining, but nitrogen seems to go up and down, almost like with salinity. But we also started seeing a rise in nitrogen from levels we had seen in the past number of years. But chlorophyll is the biggie. And chlorophyll is basically telling you that there's a phytoplankton bloom. That's what's out there. And you can see, I mean, it ruins the whole scale of the whole. This is up in Banana River, so this is where it started. This is actually this side, BO2, is across from the port there. And you can see, typically for the lagoon, 20 micrograms per liter would be a bloom event. And you can see, typically we were down below 10, 5 micrograms per liter is the normal chlorophyll numbers for the lagoon. Well, you can see we kind of surpassed that a little bit. And it really just changes the whole scale, because normally all these guys are spiking up here when we keep this scale down around 30. Okay? But putting it on this scale, you can really see. And so now this has been classified as a super bloom because it is unprecedented. It's nothing that we've ever seen in any of the years of all the years of monitoring. So bringing back this same graph, this is the graph that you saw. This is transect length. Okay? All I want you to do is look at this last column here. Okay? Now, this is 2011, so this is what happened after we sampled during this bloom. And you can see Mosquito Lagoon, because it didn't get up there till the end of the summer, we didn't really see any changes going on in Mosquito Lagoon. But as you look at the color changes in most of this area right here, you can see, and actually in this area around Cocoa Beach in the Banana River and Cocoa in the Indian River, there's complete loss of the grass beds in that area. And as well as in Melbourne, we've seen almost complete loss. Some of these beds are down to, instead of being 100, 200 meters from shore, they're going about 30, 35 meters from shore. And because the water clarity had gotten so poor, we were only seeing about 30 centimeters into the water when you put one of the Secchi discs down. We were only seeing about 30 to 40 centimeters. And now that the water has started to clear, that's where the grasses are, at 30 and 40 centimeters depth. And that's about what it is, about 40, 50 meters from shore. So we've seen huge declines, but we still have grass out there. It's not a complete loss. So we're being optimistic. So typical change, when I'd see, this is from 2009 to 2010. Typically, from looking at all those graphs from summer, winter, and going back and forth, you see we have some losses, we have some gains. The positive is green, and then we always have some loss. So, typically that's no big deal. Okay, what we saw from 2010 to 2011, loss everywhere in the lagoon, in the northern part of the lagoon. See, now your area down here, the bloom did not get down this far. But this, you can see 100% loss. So you can see all the sites that were completely lost, and we have mostly greater than 50% loss at most of our beds. But Haladuli, because Haladuli is present in all of them, is it's a prolific seed producer. So there is a seed bank out there. And Rupia, our pioneer species, another huge seed producer. So these plants, the seeds can stay viable in the sediments for years. It's really cool. And they just wait for the opportunity when there's nothing else blocking its light, and they're able to germinate. So we're hoping now, as long as the bloom doesn't occur again, we're hoping that the light will stay now, and the seeds will get enough light to germinate. So if I kind of ended my graph over here before because I didn't want to give you the other picture yet. But you can see the distance now for 2011 has dropped down to the lowest level that we've ever had since monitoring the transects. and the density. We were actually starting in 2010 to see a little bit of an upswing here, but now the density has declined. And 2011 is a mapping year. So we did get photography. We are mapping the grass beds, and the map should be available in the next couple of months. And because everything fits so well with the deep edge of the transects and the footprint of the bed, we're kind of maybe predicting that the bed is, I wonder how that raised up so much. Anyway, it's going to be the lowest levels that we've ever mapped. So you hate to end a story there. But I'm not going to pull. Everyone's been out there. You've seen it. So I'm not going to tell you that it's a different kind of story. I mean, but that's what makes the grasses so versatile. So they're very susceptible to outside things, and they can change very, very quickly. But they can also recover very quickly. And so we actually have put together a simple model of. And we've got a consortium of scientists, which Dennis Hanasek is one of them. But we have a consortium of scientists from up and down the East Coast now working on to simplify this model. But there's many components to it because it isn't just one thing that triggered the whole event. It's going to be a sequence of events because more than likely the cold possibly is what everyone's putting their finger on, is the cold that something died out, something died back that used to keep things in check. And with the salinity, and these are things outside our control. We can't predict cold, we can't predict salinity. So these are things that we're going to have to try to start getting a better handle on and be able to model it. But anyway, I had a great field crew. These are a lot of the people that helped monitor those beds endlessly all the time. Unfortunately, budget cuts. We're down to one person. Anyway, but we also have a consortium of people that help us monitor these beds. And is that going to start on its own? Oh, so we work with a number of local agencies. We work with the DEP offices. We work with the universities. We work with the different counties. We work with NASA. So we have lots of people that we like to thank throughout our presentation. So with that, I hope I've kind of got you excited about seagrasses and you want to cheer for them to come back. Thank you. Oh.